And okay, Pete,
Yep.
over to you.
Thanks, Bill. Hello and welcome to our webinar. I'm Pete Starkey, a member of the Council of the Institute of Circuit Technology, which is dedicated to technical aspects of printed circuit board manufacture and assembly. The Institute continues to successfully provide its members with opportunities to improve their knowledge of manufacturing process technologies, materials and practices, and to stay in touch with current and future developments. The future of printed circuit manufacturing and assembly will rely heavily on automation and the establishment of the smart factory. What will this involve and what additional skills will engineers need to learn? Honorary Fellow of the ICT and leading expert in this area, Happy Holden generously provided a course of 8 webinars on the theme of automation and the journey to your smart factory, based on his recently published ebook, 24 Essential Skills for Engineers. Happy's webinars have all been recorded and will be made available from the ICT. Following Happy's webinar series, another industry-leading expert in smart manufacturing has come forward to provide us with real-world examples of value creation within a modern context of manufacturing operations management and manufacturing execution systems, explaining how standards from IPC related to industrial Internet of Things-based message exchange and the interoperability of digital twins have created an environment in which everyone can participate and benefit. This webinar, entitled Software-Driven Automation, Real Values After Removal of Smart Manufacturing Barriers, is presented by Michael Ford, Senior Director of Emerging Industry Strategy at Aegis Software. Michael, with many thanks for offering this valuable supplement to Happy's course, may I hand over to you?
Certainly. Yeah, thank you very much, Pete, for that excellent introduction. Right, let's get started. So I guess at first we have to face the fact that manufacturing is in a bit of a challenging situation at the moment. There are so many different things that have caused manufacturing to have to change, to have to adapt to new challenges that have come along from supply chain, global politics, the energy crisis, environmental issues, and of course, Industry 4.0 itself that kind of throws a spanner into the works just to say, well, you need to get smart. And what does that mean? So many different changes going on. And, you know, we don't want to focus on any particular one of them because we need to be ready for anything in manufacturing. This turbulence is something that we need to learn to live with. We can't have manufacturing that does not adapt to change. That kind of thing has disappeared. We need to think about turbulence and change as opportunity. So what we need to do is to build that resilience and adopt some kind of strategy on how we're going to be able to do that. Now, Industry 4.0 today, it was created by our German friends originally about 6 or 7 years ago. It's not working, I'm afraid to say. So many people now, they kind of, you know, their eyes roll, you know, when you mention Industry 4.0. It was meant to be the panacea of new things to come. People are a little bit, you know, blasé about it now. Yes, of course, we've heard about it. Things aren't really meeting expectations. And there are reasons behind that. Apart from the marketing messages that kind of blurred the lines a little bit and people became confused about what Industry 4 actually was, we also saw some difficulties. Some of them natural and some of them deliberate, that actually got in the way of allowing Industry 4 to happen. And that was really founded with the data. So data was rather more difficult to use than people had first thought. And we want to use our data for many different uses, for many different angles, and clearly that was not possible to happen. And let's have a look at some of the reasons why. Because there are a couple of secrets in the industry that people don't like to talk about, but I do. And let's take a look at a couple of them. First of all, there has been always the need for domination in the industry. And this is not confined to electronics or manufacturing. This is how companies work. They want to dominate their market. They want to ensure that they have the maximum opportunity to get revenue from customers. Industry 4.0, well, is that a product? Is that something that you can get from one company? Would it be better if they could provide everything? Well, in reality, no, because there is so much going on in manufacturing that you don't have experts for everything. I mean, just look at the machines that you buy. Do you buy all of your machines from one vendor? Well, no. There is a difference between pick and place, screen printing, maybe a testing or inspection machine, or there's usually many, many different vendors, each with their own area of expertise, all of which work together interoperably. You pass a printed circuit board from one machine to the next, and they all work together. That's very, very nice. Well, what about the software side? It must be necessary to do the same in the software side, because we can't have one company that provides everything. We need to be inclusive of vendors that have domain expertise in, for example, quality or materials or many, many different areas, each of which will contribute to their own value to the holistic operation of the factory. And so to do this, we need to start to exchange data and allow different people to fill in the gaps that they have for their smart digital transformations. So that's the first secret. We don't want to be dependent on any one big company. The second secret we're going to talk about is standards. Now, there are many, many standards in the industry that, going back many, many years, of course, they predate Industry 4.0. So they were a kind of way of almost like de facto standards where people were using a certain technology to move data around. They wanted it to become a standard, and so they made it their own standard. Unfortunately, these standards, I mean, OPC-UA, MT Connect, there's a lot of different ones out there. They're all very good, but they are based on an ecosystem that features customization and middleware. So therefore, you need a lot of work and effort to be able to extract data from them consistently and sustainably. So why did we at the IPC think, well, we need another standard for that? Basically, for full digital interoperability, we don't want to have the barriers where you need to be dependent on customization and middleware. We want to eliminate those costs, because actually the costs of that data exchange far exceed the cost of actual software in most cases that is creating the value. And so what we wanted to do was to set out to create something based on modern technologies that would solve that problem. And one of the key problems, of course, was this middleware component. Normally in factories, going back many, many years, coding to convert data from one machine format into another, it's normal. Having consultants in there to be able to do that, it's normal. Third parties, it's normal. I did an estimate. And just off the top of my head, I kind of thought about the entire planet of manufacturing. How much are we all spending to exchange data? And I calculated it as $30 billion. Now, another publication in the market, they spent a lot of time doing an analysis of this. They disagreed with me. They said it was only 21 billion. But to be honest, inflation is on my side. I think it's going to be 30 billion. And that is just the amount of money that we spend trying to exchange data with each other, which doesn't build any value. Now, I would prefer, as an industry, that we spend money to create value and not just to enable this movement of data. So creating an environment of plug and play where we can simply plug all of our different machines and processes and operations in to a standard backbone, that would be worth a huge amount of money. Now, before we think about that, we need to understand the difference between an interface and what is IIoT. An interface is where you have two parties. They would like to exchange data, and so they get together, they exchange information. Usually it's about their product, about their data schemas, and it's often intellectual property. So there are NDAs, there are legal challenges in there, but they get together, they decide the fields, they decide the meanings of all of the data. And so they can pass data to each other one to one. This is an interface. It's transfer of data one to one. And of course, there are tens of millions of interfaces out there that people have built over the last few years. So you tend to see a lot of these interfaces being used for many different things. But the issue is that interface was developed for a specific application, and therefore the data within it is for that specific application. The Industrial Internet of Things, IIoT, is different because if you are a provider of that data, you don't know who's going to use that data. It could be one particular system, for example, an MES system. It could be another system that focuses on quality analytics. You could have 100 different systems out there looking at that data. So how are you going to decide what the content should be? Do you do the content just for one application, for 3 applications, for the most popular applications, or every conceivable application? So IIoT, we have to have a different approach to how we create the content. So the content cannot be created by a specific company for a specific purpose anymore. It has to be created with the industry in mind and all of the uses of that data. So this is why IIoT messaging is completely different from an interface that we may have come to know and love over the last few years. Now let's take a look at actually what this means, because you think, yeah, I understand that. Sounds reasonable. So what? Let's look at a case. Now here we have a machine on a production line, and we have a little bit of software, and we want to connect the machine and the software together. Great. Now it has its own special way, this bit of software, to talk to the machine. This has come from discussions between the vendors. And okay, the cost for that, let's say on a good day, and there is already an existing interface, you're going to spend about $3,000. Okay, I've got it as pounds here, but they're pretty much the same thing these days. So let's say $3,000. But if the interface does not exist, then you're going to have some customization. We often see projects that are going to look at about $50,000 to create a bespoke interface between these two things. Okay, that's a little expensive, but if needs must, then, that's what we have to do, which is fine for one machine. But even though we've got machines that look similar, actually, they're not similar inside. They use different communication mechanisms. So that initial effort to make that interface, you're going to repeat that several times if you want to talk to different machines. Now, there was one company in Europe, a telecommunications company, that did a bit of a survey for their smart digital transformation. They found that they had 12,000 different devices and processes that they wanted to connect as part of their smart factory. Can we guess how well that went? Because it gets worse. We have more than one piece of software. I mean, we spoke just now about interoperability. Well, here's some examples: MES, PLM, quality management systems, energy. There are so many different things today that we want to do with the data that we get from these machines. And as we said, no one supplier is going to provide everything. So let's say we just have 3 different solutions in there. How is that going to make things look? Well, it's not good because all of these different solutions have their own different ways of getting the data from the machines because they were developed independently of each other. And so in their discussions with the machine maker, they had different pieces of data and they got them in different kinds of ways. So this is looking a little bit more complicated, but we're nowhere near the end yet because machines now talk to each other. Closed loops, machine learning, data is passed from machine to machine so that each machine can get the context of what is going on in other places in the lines. So we have to add these kinds of interfaces into the mix. Okay, so we got there. Then our IT guys come in and say, well, hey, you've got all this data running around, and that's a major security issue. It is said now that more than half of the manufacturing companies worldwide have been targeted by a cyber attack. We need firewalls. We need rules that set out what can pass and what should not pass. So each of these my ways, you end up with a complex set of rules about how the data should flow. So that's another overhead that you need to build into your plans. But wait a minute. The machines themselves also have computers inside, and they are also vulnerable. So there was one site that we heard of where going in, everything looked okay, but everything was running a little bit slow. And on investigation, they found that the computers inside the machines were mining Bitcoin. Somebody had gone in there with a USB stick, a mining program had been put on all of these machines, and they were all compromised. So now the machines need to be protected as well from each other on this OT cybersecurity infrastructure. So again, you've got rules and rules, you've got compatibility issues. One set of rules is talking to 3 different firewalls. It's an absolute IT nightmare. How much is this costing us? Well, from our rough kind of calculation we did at the beginning, on a good day, you're going to be parting company with 100K to connect these things together easily, very easily. That's the best case scenario. If the interfaces did not already exist, you're looking at getting on for $2 million because inflation is working as well. And once you start talking about millions of dollars, and remember, we haven't created any value yet. All we've done is to transfer the information from A to B. We don't have budget for anything else. This is it. This has used up all of our effective budget. Manufacturing is not that rich when it comes to spending money in this way. So this is why Industry 4 and smart factories are so severely challenged today, and why people are simply not in the position to utilize it. Is there an alternative? Of course there is. Using the standard, the Connected Factory Exchange, I'll be talking a little bit about. This is an IIoT plug and play standard where there is one language, there is no need for any middleware, there's no customization needed. And this whole scenario boils down to 8 standard CFX connections, which would cost about $25K. $25K is acceptable for pretty much any smart manufacturing project, whereas $2 million would not be. I mean, I think we can all agree on that, yes? And in terms of firewall, very little firewall is needed because we can do everything through CFX. So this is the ideal case where CFX is working in a factory. Now, what is CFX? It's an IPC standard, which is defining IIoT-based plug-and-play data exchange. It's written, obviously, like all IPC standards, by the industry members for the industry. We have about 200 or so companies as part of this. Obviously, no licensing or anything like that. This is an open standard. We have secure end-to-end encryption, TLS 1.2, so that every message that you can send it locally, you can send it across the planet. It's going to be absolutely safe. We continue to work on new versions of CFX as we add in new technology blocks for different processes in manufacturing, going outside now beyond electronics into assembly kind of areas and other kind of niche manufacturing needs. So this is a living standard that continues to evolve. So as I said, there is a defined language with CFX. So you get the communication protocol. We used AMQP, which is created by the banking industry. You've got it on your mobile phone if you do banking. It's very, very secure. All data is encrypted. And we use JSON for the formatting of the data. But the main thing that you get, which is unique to CFX, is this one single defined language content. So if I was speaking Japanese to you right now, konnichiwa, genki desu ka? You probably have difficulty understanding what I was saying. So why, if the humans are speaking different languages and we don't understand, why do we have machines speaking different languages that we don't understand? Why not just use one? And of course, that one has to cater for everybody's needs. So we have these little building blocks that we can build together technology elements that reflect the needs of each communication endpoint. And it means that we have so many messages. Not many are required for each machine or each process, but there is the potential to use messages for almost anything related to materials, work orders, measurements, tests, performance, production completions, validation of anything, calibration. It's all in there. And so we all can speak that one language. We plug in, we read the data. It doesn't matter which machine it is, from which vendor. Everything is the same. Could it get any better? Well, yes. IPC also provides a free software development kit. So your CFX interfacing, if you're a machine vendor, is basically done for you. You just download it, introduce it into your machine software or software system, whatever you choose to use with CFX, and you then have connectivity. We also have a hardware-based CFX endpoint, which is a simple off-the-shelf Raspberry Pi computer, which has expandable hardware. This is supported soon using open source off-the-shelf. In fact, the designer of the Raspberry Pi itself is designing this with us. And so this will be open source backed by IPC as well. It means that for $30 or $50, you can create a smart machine from a machine that previously had absolutely no software capability at all. So, we want CFX to be able to exist on every machine, old or new, smart or dumb. And there's a qualification from IPC to make sure that this plug and play does work for a set of messages that we deem essential, so that you genuinely can plug things in and it works. Going beyond IIoT messaging, there is also another standard called the digital twin. And this is where we're doing the same thing, but instead of exchanging messages between machines, we are exchanging data sets between solutions. So this is more of a newer standard from IPC. It's called the digital twin, of course. IPC 2551. And again, the aim is to create interoperability between solutions, again, saving the billions of dollars of investment for continuous API interface development, all of the legal and security issues, etc. It's to create this environment of interoperability between solutions. This contains three major elements: information about the product. What did I build? How did I design it? Where's my design data? Do I have pictures of it? Do I have a 3D rendition? What's my bill of materials? What was my design intent? What is my mechanical design? How does the PCB fit mechanically within the overall thing? All of that is in the product. Manufacturing. Where is my factory? How big is it? What machines do I have? What configurations do they have? Do I have storage areas for products or sub-assemblies? What equipment and tools do I use? How they should be calibrated, etc. work orders, what products am I making, when, on which configurations, using which bill of materials, and then of course gathering the data for the so-called digital thread, which I call traceability, for materials and process measurements. The third element then is life cycle. Product goes into the market. How was it used? Was it abused? Was it dropped on the floor? Did it need maintenance? Did it have servicing? Was it damaged in some way? And so we can then go to the recycling and say we want to have reuse of certain elements or subassemblies, or we recycle the materials back to their base model. So it's covering all of these different elements, but crucially, this is forming a loop where, for example, if you want to design your next best product, to be your hit product in the market, you want to base that on how easy it was to manufacture and how effective it was in the customer's eyes. Now, all of this data is available in this circular fashion so that we can have this exchange of data freely between areas that in the past would not allow data to be exchanged. So the way it's structured is very simple. If you, for example, play a media file on your PC, you just double click it and it plays in a window. Wasn't always like that because different media files have different codecs, they have different frame rates, many different things that need to be sorted before you play it. And so these files have metadata which explain all of this detail so that players can play them. The digital twin is exactly the same. You have a data content and we want to understand what is it, what format's it in, how should I use it? Who populated this? Whose data is it actually? And are there any access profiles, etc., that I need to be aware of? So that we can have the exchange of data in a way that's very, very secure. Now, I want to mention security a little bit more because this is a very critical point for smart manufacturing going forward. There are those who say CFX is wonderful, digital twin is wonderful, send all your data into a lake, just make it all available, people can use it, going to create a huge amount of value, and it's all true. Except that there are always people who would want to take advantage of that. Some people want to make benefit, other people want to make benefit for themselves. And so we need to be aware of the security of doing this. So we have a driver toward digital transformation, but let's take a little bit of time out to consider the drive toward cybersecurity. Now, there are some key principles that I'd like to mention, which is the creation of trust, the ability to share information without violation of privacy, and establishing proof of identity. And there are some new technologies which are part of the digital twin that are essential for this to happen. First of all, creating trust. Now, there are a few people on this call. I'm sure you're very good people and very trustworthy, but would I give you my banking details? Probably not. Generally, people don't trust each other with personal data like that. Would you trust a company with that? I mean, we do. We have various companies who know our financial stuff, but do we really trust them? How about the government? Yeah, okay. Let's not talk too much about that. What about an international consortium? Well, all of these, unfortunately, have the potential for corruption. There is the potential for risk. We cannot actually trust any single individual, whether it's a person, company, or organization. So then we come to the principle of decentralization. So for the decentralization, I could pick, for example, 7 people on this call. So 7 different entities. And what I would do, I would disclose some information. Now, this could be my bank account details in an encrypted file. In manufacturing, it could be the result of certain tests or performance related to products. But anyway, I'm going to give you this bunch of data. I'm going to give the same data to each of the 7 entities. Then maybe one of my customers wants to access that data. They will have a key from me to be able to access this, and they will request that data. And they will request it to all 7 of these entities. And in this example, we have 1, 2, 3, 4, 5 entities that responded positively. So they came back with the same response. One of them didn't reply. We heard nothing. Okay, we'll ignore those for the minute. But one came back with a different reply. So the assumption is statistically that the majority response is trustworthy. And the one which is the odd one, they probably have been hacked. So this is the principle of decentralization, the ability to statistically get back the majority result, which is consistent. And therefore we know that we have the right data. Now, if only there was a technology that would kind of wrap this up in one word. Oh yes, blockchain. This is blockchain. This is exactly how blockchain works. So it's not a wonderful magical technology. This is actually all it provides. It provides this decentralization. And there are hundreds of buzzwords around blockchain that people like to talk about and argue about, essentially related to who are these entities? How would we choose them? How do we pay them for participating in this network? And so there's a lot of those discussions. But the principle is very simple. And it's a statistical principle that no more than 50% of these entities can be hacked. And in the case of Bitcoin, for example, there can be hundreds, if not thousands of these entities. So the more entities you have, the more secure you may think you are. So this is the principle of decentralization. The W3C has created decentralized identifiers so that, for example, for me, maybe I store my fingerprint, I create a digital ID of myself. This may be some kind of code that we put onto a product. It may be burned into a chip. It could be any kind of identifier. And we can then globally register these as global identifiers that people cannot copy or clone in the digital realm. So these self-sovereign DIDs are self-generated. They are globally unique, very, very secure, and can be universally used to identify things, people, and data sets. So this is a technology that assures that we know who we are. The next key technology I want to introduce is verifiable credentials. Here we have the need to share information between 2 parties, but we don't want to disclose our intellectual property. Now, as an example for this, let's just say I would like to go, I'm in the US, I'd like to go to some kind of theater or event, or even just enter into a bar. Well, the British government knows me. It knows all of my medical records, my financial records. It knows everything, to be honest. Maybe it knows more than I would like them to know, but I can't get away from it. They know my private data. I don't want anybody else to know it. So let's say I go into a bar and they say, hey guy, you need to be 21 years old. Okay, I look more than 21 years old, but let's just pretend he thinks I'm a young guy. Now I have to hand over my ID, my passport. It's got my address in there. It's got all kinds of other information in there that he could just copy. I don't want him to do that. I don't want him to clone my identity. I would like to be able to prove that I'm eligible without giving any information. And that eligibility may be my age, it may be my COVID status, it may be all kinds of stuff. But basically, I want to be able to give him my unique ID, my DID, that is my fingerprint, or iris, or whatever it may be. I may be trying to enter the USA. And again, this is another scenario. But I want to be able to give that single ID. That little device will then connect to my private data, which is stored securely in the cloud using the distributed storage, and it's going to ask a question. So it's going to say, well, this ID has just tried to get entry to this event or this country. Please evaluate. And a little bit of software will look at the rules, it'll look at my data, and it will make a decision to say either yes, you can enter, or no, you cannot. So then the guy on the door at the bar, he will get a message coming back to say, yeah, this guy can have a drink. Or it will say, no, you need to turn him away. But my private data, the reason why I was not able to go there, was not disclosed. So this is a mechanism to exchange facts without disclosing data. So for example, for provenance of products, was my product made in the USA? What is the rule for that? Does 70% of the assembly need to be done, or a certain amount of the material come from the USA? Well, the rules change from time to time. But if you have the traceability records of your assembly, as well as all of the traceability records for the materials that you use, that is the data that can remain private, even on premise. And a verifiable credential would be able to evaluate the answer to that question and decide what summary of data or what facts would then be disclosed that would satisfy the need. So this verifiable credential is an amazing new way to be able to exchange data and information without exposing private data or IP. And this is being used, at least starting to be used, in a wide variety of uses. These are US examples for border protection, airlines, retailers, all kinds of areas right now. We're even replacing the green card for entry into the US. So, you know, this is a very exciting technology that a lot of people are using. And of course, we would like to use that for the exchange of manufacturing data within IPC digital twins, ensuring confidentiality, privacy, but always identifying who is the owner, who is responsible of data, and the ability to share information. So we've been talking about really, because if you were to buy a solution that makes value in manufacturing, if you want to be smart, you would normally just take all of what I've said for granted. You'd say, well, yeah, I need data from this machine. I would like to use it in my wonderful bit of software. What's the big deal? Well, I hope you understand now that there is a big deal behind that, but there shouldn't be. If we use IPC standards to create this interoperability, we can save the billions and billions and billions of dollars that it would need for us to all be smart and secure together. And this is very, very important because we don't have a lot of money to spend. We certainly don't want to waste anything. Anything which is spent to try to connect systems through middleware or customization is a waste of money. It's not creating value. What we're going to look at now are some real values that we create from the use of this data. There are three kind of layers for this. The first on the shop floor, where machines want to talk to each other. We mentioned closed loops earlier. These used to be pretty niche applications that were extremely expensive because people had to create interfaces. Now with IIoT, with CFX, all of these are much, much more affordable, much more available for many different kinds of machines and processes. Then you want to collect the data from the shop floor to the factory level. And you have all of your favorite factory level functions, traceability, quality, all of these different things that require data. They can all now get their data. And this, we call it the MES layer, but it's basically the factory layer. And here we are creating the contextualization of what is going on, putting everything together, understanding root causes, understanding events, and understanding then what actions we may need to take. But the data doesn't stop there. It then goes into a whole other layer of analytics, where, for example, our so-called AIs can make much more analysis of stuff. They're not dealing in the real-time aspects. So the factory is, you've got a certain time to make a decision or find something because it's happening right now and you don't want to delay anything. But at the higher level, you have the data, you have time to do the analyses, and you're able to spot trends that otherwise would not have been noticed. So what makes artificial intelligence smart? Big data. That is not a lot of data necessarily, but it's different types of data from all aspects of manufacturing. With CFX, we get that all in a detailed form in one language. But that data is no good by itself. Contextualization means that you are able to take the data points from different machines or processes together with information about the product, maybe about the production configuration, and all of the other things that we talked about in our digital twin, but all of that together to understand what it actually means. I mean, remember the Terminator movies? You know, it was a software AI that was meant to protect humankind, ended up destroying it. Why? Because it lacked contextualization. It solved the problem of eliminating conflict by destroying everything. So, you know, that's just a classic, simple example of why context is important. But all algorithms that we develop are only useful if they work within the right context. So as we create new AI applications now and in the future, this layer of contextualization is vitally important. It's not just the raw data from machines. If we only look at raw data, we're losing 80% of the value. If we build context at the time things happen, we gain the full percent of the value, and we reduce the processing power needed by AI applications that otherwise would have to reverse engineer the context. And so we reduce processing time, you know, from, you know, by at least 2 orders of magnitude. And so that, you know, relates to faster response and much lower costs. The rise of AI software is with us, but I like to think of it as being founded in human intelligence. We are the ones who are really creative, imaginative, and innovative. The problem, at least for me, I have a limited attention span. I need feeding from time to time. I get distracted and tired. So I'm not 100% all the time. With artificial intelligence, that's not the case. It just goes and goes and goes. And so it will do billions of calculations where, you know, I would have got tired long ago. So we have intelligence from the human that is now being processed by the computer. We are the creators of that intelligence. So the intelligence is not created by the computer. It's programmed by the human into the computer. And if you've got that contextualization right, we're not going to die. We're actually going to get benefit from how the analyses take place as we look at all of this data in the different ways. So this is how today AI is doing our heavy lifting for us. We have the ideas, the AI carries it out. And that's basically what it is. Now, there are a lot of areas in the manufacturing that we might want to look at. Digital manufacturing engineering, so understanding the product. So we need to know what we are doing, what we're supposed to be doing. That always helps. That's a good bit of information to contextualize against. Materials. We may be using the ones that were defined in the design. We may be just using the ones that were cheaper and freely available at the time. MES, we need to ensure that every process is working properly. It's been set up properly, that things are executed in sequence correctly, and any exceptions like a failed test is dealt with appropriately. So it's the management of all of the different processes that go on across the shop floor. And, you know, the vast majority of this can be automated. Bringing then the information back as intelligence, we enable then the trend analysis, the visibility, the dashboards, etc. And of course, that is then based on our IIoT ecosystem, CFX. But as we said earlier, there are many different other applications as well. Planning, quality management. A factory cannot do without these things. And even beyond manufacturing. I mean, initial manufacturing, it is said, is only going to be half of the total manufacturing effort in the future, where we need to be recycling at least as much as we're manufacturing in order to build a sustainable economy. So repurposing things, refurbishing them, changing products from one thing to another, maintaining them, repairing them is going to be of equal importance. So this is where we can have a lot of value. Let's take one very simple, basic example of how to become smart in this area. And it's looking at material management. Oh, hang on, we've got a system for material management already, don't we? We have ERP. ERP is managing all of the materials, the ordering, and making sure the materials are delivered in time for production to start. Well, that's true. There's nothing wrong with ERP, other than the fact that it basically deals with how many, part numbers and how many of each part number we have. It may know that those parts are in the warehouse. It probably has issued them to manufacturing and assumes that they are being consumed or whatever by a simple backflush process. But we have problems with this. We have attrition, we have scrap, we have waste, spoilage, we have errors that are being made. We have all kinds of things that together contribute to create unexpected internal material shortages. ERP says, yes, the materials are there, this quantity, no problem. The reality, physically, we can't find them. What happened? And so if we look at smart MES, material management, we can assign identities uniquely for each carrier of material or even individually for materials. We can track exactly where they are, the status that they are, how many have been used, how many have been spoiled, part used materials, exactly where are they, and in use, we can associate specific materials to each specific product to get that traceability. So we know the exact quantity and location and status of every piece of material. What does that mean in terms of benefit? Well, first of all, we don't have to do any stock checks anymore because we have a very consistent inventory level that is recorded by smart material management as compared to the physical. So as long as those two things are in sync, then we never need to do any manual counting, which is good news for those who have to do the job. But let's have a look at some other specific benefits. After introducing smart material management, okay, at first there's a little bit of a shock where we realize, as we're counting the materials that we've got and putting them all into a system, we realized how out of control we were. And we end up writing off huge amounts of money. I've seen $1 million been written off in a 1-year cycle by a consumer products manufacturer in Mexico. And it happened every single year. But anyway, you need to face reality. And then as you get to understand exactly what are the causes of these problems, then you get to be able to start to fix them. And you find that a lot of these big problems were internally created problems where materials had run out in the middle of the night because of some spoilage issue on the machine. And then a reel of components had been taken from a different kit intended for a different product to keep the machine running so the machine operator's happy. But then the next kit starts, the machine stops, and you realize there's been a loss of material. So these are cumulative errors that are now being resolved by the ability to understand exactly where all these losses are. Now look at the downtime of operations in manufacturing as a result of this knowledge. Here we were facing a lot of disruption for the apparent loss of materials. But once you are able to know for absolute certainty that the materials are really there, because you know the serial number, you know the quantity, you know the complete history, this gets to pretty much zero. Whereas before, many, many hours were being lost of production time simply because we'd lost the material or there'd been some kind of internal issue. Let's look at the inventory level that the factory's holding. How much had ERP been adjusting its stock levels to make sure that materials were available, even when the accuracy was not there for the inventory of materials in the factory? So it had bloated its inventory, typically doubling the amount of stock on inventory that it would hold, simply to ensure that from one stock cycle, stock check to the next, there would be no unexpected shortages. So as we take control of materials, we're able to bring that stock holding down. Now, these things are transferring into real benefit, aren't they? Because we're reducing the investment in bloated inventory. We're increasing productivity on the shop floor. So this is not just a game of, oh yes, we've got the data in a computer, doesn't it look nice? Actually, these are real world benefits. People, the people who move the materials around the factory. You know, it's not a great job, but the worst part of it is not the moving the materials. The worst part is the boredom that you have between the peaks of production requirement, where you frequently see people just sitting around, just got nothing to do. When you're in control of your logistics, you're able to smooth out those peaks using just-in-time material delivery. You can then repurpose people to actually do a cycle count within the warehouse, for example, utilizing their time. There's no stress, there's no pressure. Actually, their life becomes much, much nicer. And of course, the amount of workload that you potentially need reduces. So you're saving cost and improving that kind of work style. I've been to companies here in the UK that use smart material management, and they said out of everything that's happened to them, this is the one technology that has enabled them to survive. You know, all that chaos we talked about at the beginning, this was the number one contributor to their survival and success. This is not a trivial amount of benefit that we're talking about. We're talking about halving the amount of investment of materials. We're talking about improving productivity by many, many percentage points. So, you know, something that's as simple as just reading a barcode on a reel of parts translates into a huge benefit for the operation. So this is an example of a basic application. Let's look at a more advanced case. One of the biggest problems that we have, let's say we want to make a product, maybe a sensitive product that would be made by a manufacturing partner who may not be in the US, may not be in Europe, maybe they're in China, maybe they're in Vietnam, who knows. There is a risk that giving the data about the product to that manufacturer, which of course they need because they need to manufacture the product, so they need to know it, but they could make their own. They could steal the technology. Somehow that data could get intercepted. And of course, this has always happened. But in the past, this was physical re-engineering. You go into any company and they will always have their competitors' products there. And they're taking them apart to see how they work. How much did they cost? Where did the materials come from? It's normal. But that takes months, if not years. In the digital domain, it happens in seconds. This is a problem. So there is a combination of use of IPC standards. So and think about the digital twin while we're thinking about this. The design data, IPC 2581, we also know it as DPMX. This is our single file representation of our product. Do we want to share that with manufacturing site and send the data to the machines? If we're operating in the US or in Europe, maybe that's fine. But at least we want to transfer it securely. And so using CFX messages rather than email is a great way to do that. Email has been hacked many, many times and continues to be so, whereas CFX is a very, very secure way of transferring that data file over the internet. And in fact, it goes straight into your manufacturing system and it hardly requires any human involvement at all. But let's go one step better. What about the ultra secure use case? This is where we don't want to send the whole data to anyone in manufacturing, but we need to be able to send certain portions of the data to certain machines, or let's say other software systems in manufacturing, so that they know how to make the product. Maybe they will be ordering the materials, maybe they will be setting up the machine for the inspection, whatever it may be, setting the placement program, for example. There are ways that production machines can access certain areas of the design data depending on what they need. So an inspection machine may need the top and bottom surface characteristics in order to know what to look for. So it will request that data in the form of a verifiable credential. This is my ID. This is the product ID. send me the information that's relevant only to me without exposing the rest of the IP. I will do my calculations. I will not store it on my hard disk. I will not let a person look at it. I will automatically program it. And Koyoung is one of the examples of inspection machines that does this. I will completely automate that programming process. I heard what I need to do in terms of my share of the production work from my local MES system, and the rest of it I've derived in this secure way. Once I've used the data, I free it in memory. Nobody ever got to see it. So now you can be making your very sensitive product in a manufacturing company who may not necessarily be totally trusted, but you are able to do that and have perfect products being made without that disclosure of the whole of the design data. So this is an advanced use case that we're looking at right now. We have several companies interested to do this, and this is an example where we combine the IPC standards of digital twin, CFX, the design 2581, etc., and using these new technologies of distributed IDs and verifiable credentials. This is just one example. Let's have a look at another, energy management. Energy costs money. I think we've all got to grips with, especially in Europe, where energy prices have gone up by 4 to 10 times in the recent past. But as we have more renewables, we have cycles for energy consumption, which are fairly predictable, but they go up and down enormously. On a sunny day with a bit of wind, we don't use any energy from nuclear or coal or gas. Whereas, like it is right now here, with the rain beating down and it's cold and wet and dark, we're pretty much dependent on them. So the change of demand is extreme, and it's becoming more so as time goes on. What if we could profile the energy consumption of all of the processes in manufacturing? What if we could ask machines to go to sleep when necessary? What if we could make sure that we would wake them up in time for the next product that arrives there in 5 minutes, 30 minutes, an hour? Different levels of sleep to reflect more and more energy saving. What if we could plan our manufacturing to be able to take advantage of times when electricity cost is cheaper through these dynamic tariff incentives? We become a lot more sustainable. We have a lot less effect on the environment. How can we do this? CFX has these messages built in. All the definitions of the power states, the sleep states, the energy consumption, it's all included. So this is an advanced application where you might want to develop or have some bit of software somewhere that's looking at your energy profiles. What about maintenance? If you go into manufacturing and you hear a noise, a humming noise, vibration, you put your hand on a motor, it's hot, you know that there's something going wrong with that motor. Well, there are sensors for that. You can measure the stress, temperature, vibration. There are CFX messages that convey that information about specifically defined elements within those machines, so that you can start to use that data to plan when the sub-assemblies, motors, fans, whatever, need to be maintained or replaced. This can be done through analysis of electrical current as well as the different vibrations, etc. So then you can start to ensure that you do the maintenance at a time that's convenient rather than when the machine breaks down. So this is not a new idea, but with using CFX, you can funnel all of the information from every machine through one channel, the CFX network. That can then be used directly by machine vendors. You have the freedom to select a supplier of predictive maintenance software. It's open. This is your interoperability. So this, again, is another advanced application. I could talk for another 2 hours, 3 hours. How long have you got? But we don't. We have a couple of minutes left. But what is next? These are just a couple of examples, one basic and a couple of advanced examples where the use of data that provides this interoperability of connection between different machines, devices, endpoints, and software solutions, this really starts to create benefit for us. And this is what digital transformation, smart factories, industry 4.0, I don't care what you call it, this is where the value is created. Once we solve that problem of how to get the data, which seems to have preoccupied everybody for years, once we sort that problem out, as we have done, then we start to create some real value. So for those who are interested, maybe you've got your own projects ongoing, or maybe you would like to start something, IPC standards committees are open to everyone. There's no cost. You just simply join and start to participate, contribute where you like, comment where you like. But please start to use these technologies, understand how they really start to reduce that cost, that waste of cost in getting operations automated through software becoming smart. That's what we want. We want to make things better. We want to make things cheaper. We want to have answers so that no matter what the world may throw at us next, that at least in manufacturing, we are ready for it. That's the principle of getting smart. So yeah, I'd just like to finish off and say thank you very much for your time watching this, and please contact me if you have any questions or follow-up. My email address is there. I'm happy to help you in any way with your projects and introduce you to people within IPC and all of these other technologies that we've talked about. Okay, so I'll finish there. Thank you very much indeed.